Hello and welcome to lecture 29 of our Essentials of Semiconductor Device Physics course. In this lecture, we're going to conclude the analysis of a p-n junction in equilibrium. So last time we proved that the condition of equilibrium for currents indeed entails the condition of equilibrium for energies, as we already expected from the analysis of lecture 9. Now this time, we're going to find an expression for the electric field and the width of the depletion region in terms of the concentration of doping atoms. So to do that, to find the electric field in the depletion region and the depletion region width, we need to know how the p-n junction was doped. So we need to know the doping profile. And we're going to assume that the doping profile is uniform on both the n and p sides. So we're going to assume that we have a uniform concentration of ions on the n side and a uniform concentration of ions on the p side. The doping profile does not have to be uniform. We could have other kinds of doping profiles, but if we understand how the electric field and the depletion region width can be obtained assuming uniform doping, then we are well placed to understand how it can be obtained assuming more sophisticated doping profiles. So we're going to assume uniform doping, so we have a uniform concentration of ions on both sides, and if the concentration of ions is uniform and the exposed charge within the depletion region comes from the exposed ions, that means that the concentration of exposed ions and hence the concentration of charge is also constant or uniform within the depletion region. So recall that these are the exposed charges, so we have a constant concentration within the depletion region, and then this concentration goes abruptly to zero outside the depletion region, because outside the depletion region all ions are covered, so there is no local net accumulation of charge. So these charges do not contribute to the formation of an electric field because they are all covered. And we also have a similar situation on the p side. We have a uniform concentration of charge, but now negative charge, which goes abruptly to zero outside the depletion region. And also recall from lecture 25 that Nd denotes the concentration of N doping atoms, and Na denotes the concentration of P doping atoms. So if we have an Nd concentration of N doping atoms and each ion contributes with a fundamental charge, then it follows that the concentration of charge must be Nd times Q. And the same idea applies over here, but with the concentration of p doping atoms, and the charge now is negative. Now, since our problem is to obtain the electric field created by these local charges, we need to invoke the physical law connecting the electric field with the charge, and that is Gauss' law. So here we have the divergence of the electric field. This term is the concentration of charge, and this is the semiconductor's permittivity. Since our problem is one-dimensional, then the divergence reduced to a single partial derivative, and then we have this form of Gauss' law, which we are going to use in this lecture. Okay, so to obtain the electric field, we need to integrate this equation here. And to integrate this equation, we need to write explicitly the spatial dependence of the concentration of charge, and that's what's done in this box. So the concentration is zero outside the depletion region, that's this term. The concentration takes this value between this coordinate and the origin, that is this term over here, and the concentration takes this value between the origin and this coordinate, that's this term over here. Now, since within these two domains the concentrations are uniform, that means that when we integrate the electric field within each of these two domains, we're going to get a linear dependence of the electric field on x, because within these two regions, the derivative of the electric field with respect to x is a constant term. Okay, so if we integrate this equation, assuming this value for the concentration, then we get this expression where this term here is the electric field evaluated at the origin. So if we plug 0 for x, we have 0 here, this term is 0. That means that the value we obtain must be the electric field evaluated at the origin. And if we solve this equation, assuming this value for the concentration, then we get this equation again in terms of the field evaluated at the origin. So now we need to apply the boundary conditions. So we already know that the electric field is confined within the depletion region for the same reason that a field is confined within a capacitor. So we can then impose that the field at the borders, at the edges of the depletion region is 0. So this is the field at this edge is 0. So, and this term is stating that the field at this edge is 0. So these are the two boundary conditions that we need to use. So using this boundary condition here in this part, so we plug minus xp here, then this term will be 0 due to this condition. Then we're going to have minus xp here, so we have minus with minus positive, then we move to the other side, and we get this expression for the field evaluated at the origin. And if we apply this boundary condition over here, then we're going to get xn here. It's going to be 0 because of the boundary condition. We're going to get xn here, move to the other side, and we end up with this expression for the field evaluated at the origin. So this is obviously a linear relationship, so it's a line. We already know that the field at this point is 0, so this equation is telling us that the field is increasing linearly until it reaches its value at the origin, and then it decreases linearly until 0. So of course this number here is a negative number, as it can be seen explicitly in these two expressions. We have the negative sign here, and all terms here are positive numbers, and the same here, we have the negative sign, and all terms here are positive numbers. So the field at the origin is a negative number, and that makes sense. We set the x-axis to the right, and we know the field points to the left, so the field must be negative because it's pointing to the left. Now, since we have two expressions for the electric field evaluated at the origin, that means that this term must be equal to this term. And that entails this equality, which entails this relationship between the two coordinates and the concentrations of doping atoms. So now we're going to store this relationship in a box. Now we can connect the electric field with the potential difference by recalling that the potential difference is the work done by the field. Now, if we integrate the field over space, in other words, if we calculate the work, then we are calculating the area of this triangle. Since the field has a triangular profile, it's linear on both sides, then all we need to do to connect V0 with the electric field is to write the area of the triangle explicitly. So we already know that V0 is a positive number, so I'm writing the area here. This is the base of the triangle. This is the height of the triangle, but I'm setting here the magnitude of the electric field to get a positive number, since V0 is a positive number. And we divide by 2 then to get the area of the triangle. So with this form, we have a very convenient expression for the electric field evaluated at the origin, because now the field depends on V0, which depends on the Fermi levels of the N and P doped semiconductors before the junction was formed, and we already know how to calculate these Fermi levels from the concentrations of doping atoms. So to get a better notation, we're going to now express the width width of the depletion region explicitly in terms of W. Remember that we define W as being the width of the depletion region. And this expression we can simplify it using the expression for the electric field. So from here to here we are just using this expression here for the electric field, and since it's the magnitude we can lose this negative sign. And now we solve for W here, for the width of the depletion region, and we get this expression connecting the width of the depletion region with the electrostatic potential difference and one of the coordinates. Now we can get rid of this coordinate by recalling that by definition the width of the depletion region is given by this coordinate plus this coordinate, but they are related to each other. So we can use this expression here to express xp in terms of xn, and that's what is done from here to here. We replaced xp with xn times nd divided by na. So we can recast this sum in this form here. So to make some space in the screen, I removed some of the equations and left only the most important ones. So now we have everything we need to find an expression for W in terms of parameters that depend only on the concentration of doping atoms. So here we are almost there, because the only term we don't know is xn. But here we have another expression for xn. So we can solve for xn here. So we move xn to this side and w over here and replace here. So that if we do that, we get this expression for w. So we replace this xn here with this xn expressed in terms of all of these divided by w. So we move xn to this side and w to this side, we get this expression. Okay, so now all we need to do is to rearrange this expression a little bit. So we take w, move to this side, and we get w squared. Take nd, multiply over here, it's going to cancel with the numerator, we end up with this expression. Multiply nd over here as well, get this term here. Then we take the root square, and we finally get an expression for W, which depends only on the concentrations of doping atoms. So these concentrations appear explicitly here, but they also appear in V0, because V0 depends on the Fermi levels of the N and P semiconductors from which we form the p-n junctions. So in a few moments I'm going to remind you of how to obtain these two parameters from the concentration of doping atoms. And also notice that this is the permittivity of the semiconductor. So this term depends on which semiconductor was chosen to form the p-n junction. And now if you want xn, xp, and the field at the origin also in terms of parameters of the semiconductor and the concentration of doping atoms, we already have everything we need. For example, if we want xn, we can use this expression here. So for xn, as we've already done, and then everything on this side here, we already know how to calculate in terms of parameters of the semiconductor and concentration of doping atoms. And if we want xp, then if we have xn, we can calculate xp easily using this expression, and we can calculate the field at the origin using this expression. Just as a reminder, we learned in lecture 25 how to calculate these two parameters in terms of the concentration of doping atoms. These are the expressions we derived. Then we can subtract one from the other and get this expression here, which we simplify to obtain this expression. And recall that Ni and Pi are the concentrations of free electrons and holes in an intrinsic semiconductor. And that we learned in lecture 24, that this product is not altered by doping, and it depends on the band gap and these two parameters which depend on the effective mass. So these parameters here depend on the temperature, effective mass, and band gap of the semiconductor. So there are parameters that depend on the semiconductor of choice, and we already know how to calculate them if we know the band gap and the effective masses. So with that, we have concluded our analysis of p-n junction in equilibrium. This was not an exhaustive analysis. We could, for example, go on and calculate the capacitance of the p-n junction, but I believe that if you follow the logic developed here, you are very well placed to advance more in your studies and understand how other parameters are also obtained from the concentrations of doping atoms and also parameters of the semiconductor. Okay, so we've concluded our analysis of p-n junctions in equilibrium, and the next time we're going to begin our analysis of systems out of equilibrium. And we need to learn how a p-n junction behaves out of equilibrium, because when we take a p-n junction and connect it to a circuit, in other words, when we use a p-n junction, we are taking it out of equilibrium. So we're going to have to learn what happens to this kind of system out of equilibrium. And we're going to begin our analysis by introducing the concept of quasi-Fermi levels. So I see you next time.